Hello, time for another acoustics lecture. This one's going to be on noise and vibration control. That MEP there is mechanical, electrical, and plumbing. So there could be all kinds of noise and vibration control, but we're mostly going to focus on building systems, the mechanical, electrical, and plumbing of buildings. A lot of these pieces of equipment you'll find in other places like pumps, condensers, and all that kind of staple mechanical equipment. So the MEP, it's mechanical, electrical, plumbing. Mechanical and plumbing, this often falls into the duties of the mechanical engineer, what is called HVAC. So I looked it up on the Bureau of Labor Statistics. This is the single largest category of jobs for mechanical engineers. I believe something like 25, if I remember, it's been a while since I looked this up. I think something like 25% of mechanical engineers end up becoming building services engineering. And I say this with a lot of respect. It's kind of I've never heard anybody else say this, but I say it's kind of the nursing of mechanical engineering, because nurses can basically go anywhere and they're needed. Mechanical engineers that do building services engineering, it's probably the most likely that you're going to go to some place and that kind of a job would be available there. Any town of any significant size where there are people there designing and building buildings, then it's likely that there's an MEP engineering firm. And there are some pretty behemoth architecture and engineering firms. So they have architects, they have engineers, they have not just the mechanical and electrical engineers that do the MEP, but they also have the structural engineers, the civil engineers. They do interior design. They might have AV designers. They could have acoustical consultants there. I've kind of noticed a trend to these bigger and bigger companies. It seems like they keep merging together to keep forming these bigger and bigger companies. Maybe that's just the future, or maybe it goes in cycles. I don't know, but I've noticed that. Anyways, moving on, the E is for electrical, and obviously electrical engineers are going to be the ones that are doing that. In red here it says HVAC, so mostly the mechanical engineers systems. These are a primary, if not the primary source of noise and vibration in buildings. I don't want the electrical just to be ignored either, because electrical can be a significant source of noise and vibration. Transformers are the worst offenders in their realm, but things like ballasts and lights and stuff like that you need to be aware of too. Dimmers. There's, I'm not just talking like the little dimmers in your light switch. I'm talking like big dimmer racks for a performing arts facility, something like that. Let's talk about data reliability a little bit. This is from ASHRAE. It says here, the first bullet point, that laboratory test data can be plus or minus 2 decibels. That's the accuracy of that type of data. That's really the best. A lot of the manufacturers have impressive noise measuring facilities. I've been to Train's facilities, and they have an entire huge building where they have all kinds of anechoic chambers, and the big ones that can go down to below 50 hertz. So, something like a 30-foot cube minimum space. There's a relation between how big the room is and how low it can go. I forget the exact numbers, but something like that. I think theirs are even bigger than that. And so they want to put the biggest rooftop units that they build. Some of them might be in the hundreds of tons. They want to be able to put those in there and measure them at many different operating conditions so that they can provide data to the acoustical engineer that will make sure that the background noise criteria is met. Some manufacturers are much better than others in that regard. Some of them barely publish anything. I'll talk about that a little bit more in a minute here, but first let's talk about this next bullet point. So correctly performed estimates, the accuracy of that is typically plus or minus 5 decibels. I'm going to talk about a little exception to that down here, but before we get to that, let's cover this one. So conservative design practices should be followed. So this means if you have a really critical job, it's a concert hall, then you're going to want to design so that the worst case scenario, that very worst day of the year when they need the most cooling, then it's going to be 5 decibels below the criteria. So then even if you performed everything correctly, you still might get plus 5 decibels of what you predicted. So if you do that, that would be a conservative approach, and that would make sure that you would always meet the criteria. So down here, ASHRAE 87 fan calculations. That's this exception to this. So first let me say your reading assignment, the ASHRAE Handbook on Noise and Vibration Control. That chapter, it comes from a handbook. There are 4 handbooks published by ASHRAE. If you've taken HVAC classes, you're probably familiar with these. Every year, they cycle through publishing a new version of these. So 87, 91, 95, and so on for that handbook. And if you go all the way back to 87, they published these fan calculations for predicting the noise from fans. And they found that the inaccuracy or the accuracy of that was plus or minus 10 decibels. So I think because of that, they removed it from their publication. It hasn't been published since. But it is still the best prediction tool, just if you're starting from scratch. So I before I said I'm going to get to something later, I want to kind of tier for you what's the best and then the levels below that. I think we already said that the best is to get laboratory test data. And it might be a little bit difficult to get that. A lot of times the mechanical engineer will end up calling his rep for the equipment that they use in their designs, and that rep will, he might have software. The mechanical engineer actually might have software for some companies. Then the rep might have it, or it might have to go all the way back to the factory, or it might not be even that it might be that nobody even in the factory has what you want. But the ideal would be to track down that person that can get you that data as long as it exists, the laboratory tested data. And then if that's not available, the second best option is to, if there's a very similar piece of equipment, you use that data and adjust it a little bit. The manufacturers themselves do that a lot. They're not going to test every piece of equipment for every possible condition it might operate under. So they're going to test, some increments of that system, of that equipment's range, and then they'll interpolate or extrapolate outside of that to get the data that is needed for that particular design. And I mentioned that some of the manufacturers are much better than others for publishing data. And say you get one manufacturer, I won't say who the bad ones are, but say you get one manufacturer and they're just like, sorry, we don't have sound power data for this equipment. There's a big handful of manufacturers that will produce some pretty standardized, kind of like almost off-the-shelf equipment, like say a packaged rooftop unit, a They'll have a 10 ton, a 7.5 ton, a 5 ton, a 4 ton, a 3 ton, and so on. And basically all the manufacturers produce something like that, and they're all fairly similar. So you can, if you know, if you have data from one of the good manufacturers and it's like a 7.5 ton unit and same CFM, that'd be the cubic feet per minute of air supply and all that, then you can just use that other manufacturer's data, or you can adjust it a little bit. Say like, I know this one has more pressure drop, so the noise is going to increase in this way. That's the second best option. And then the third best option is just if you really don't have anything to go off of, and this happens quite often, you just don't have anything good to go off of, then you can turn to predictions like this. And I'm gonna I said lots of manufacturers use this. Sometimes I will see the data that a manufacturer provides for, it's the sound power data for their equipment, and I will see right there in the small print that they say that they use that ASHRAE 87 calculations. So they're using it. I know, like, I use it. It's useful. I know a lot of consultants use it just because there's not really anything that's better than that. But there is a good amount of error, so you'd want to be conservative when you're designing using this. I mentioned this just in passing. Maybe you comprehended this, maybe not. It's okay if you didn't. So I mentioned if you have a really critical application and you want to design 5 quieter than the criteria, or maybe in this case you even want to design 10 quieter than the criteria, that would be this conservative approach. But let me just reiterate the part about only do that when it's really critical. For one, if you're, say you're always over designing things, and it's maybe not this, just in your wall assemblies or whatever you're designing. If you're always over designing things, then the client isn't going to want to call you back. So you want to be on target. And even though you know that there might be a pretty big amount of error, a lot of times consultants will just design just right to hit that target. And if it ends up being a little bit more on, say, like the very hottest day of the year, that's okay, because most systems today have VFDs in them. So it's variable frequency drive, meaning that they don't just have to run at 100% or 0%. In the past, or less expensive equipment that doesn't have VFDs, you probably lived in a house at some point that had this, but everybody just kind of sits around and it's quiet, and then all of a sudden the furnace turns on. It turns on 100%. It's just like loud. Everybody notices it. And it keeps going until everybody's too hot. And then it turns off, and it's all of a sudden really quiet again, and it keeps cooling down until everybody's too cold. And all of a sudden it turns on again, and everybody jumps again, and it starts the cycle all over. Well, nowadays, most equipment doesn't just turn on 100% and then turn off. It's usually they can ramp up to be whatever's needed. So because of that, and because systems will be designed so that on the worst case scenarios are the only time that it's running at 100%. Like it might only be a couple days out of the year that it's really running in its maximum capacity and the noise is the greatest. So most of the time, even if you are designed right on and it ends up being 5 decibels higher than what you designed, then because that VFD, it kind of saves you in the end. Let's see, probably blobbed enough about all of this page. This page here, we have the main transmission paths. We're just trying to get big picture stuff here. The 3 main paths are going to be airborne, ductborne, and structure-borne. So we have this pieces of equipment here. There's looks like a pump is in there and a fan is in there. So the airborne is just going to be, these are producing noise. It's coming out through this louver, and then that sound is just being transmitted through the wall, right? That'd be those noise reduction calculations we just did. That's the airborne path. It'd be like casing radiated. You don't have to have that louver. You might just have a casing over it. When you have a louver, when air needs to be brought in for cooling, some like or it needs to be taken out for exhaust. But you might have some units that are just a casing over them. They're not having outside air or an exhaust. And that casing radiated would be airborne. The ductborne, that's the next pass. So here we have this fan, looks like two of them here, but the supply would be this one. So it comes out here to a diffuser. That fan noise is traveling through the ductwork, and it comes out here to the receiver. That would be called ductborne. Now that I look at this a little more, see the return path, this happens. So it's having a return, an open return here. Basically, it's using this entire space as a return plenum. So the return path is going to be this one here. So this is pretty characteristic of return systems return in systems like this. They have a return ductwork that just punches in above the ceiling of the space, and then it just ends. And there's probably a grill or grills all over in the ceiling. So the supply is ducted the whole way. That comes down into the room. It cools or heats the room, whatever's needed. And then once it's done that, it returns back through a grill in the ceiling. And then it comes up and goes through this. And then here it's coming back into the unit through this return opening or an inlet. Note though, the arrow is pointing in the other direction. So we're worried about noise here. Sound travels so much faster than the air is moving that it almost doesn't even matter. You don't treat the supply in any way different than you would the return. Even though the air is going this way here and the air is going this way here, for both of these, you just calculate that the noise is going this way. So remember the speed of sound was 1,125 feet per second, and a typical HVAC system is going to be, it can be a pretty wide range, but say like that 1125 would be a good number, kind of middle of the road, but it's not feet per second, it's feet per minute. So you have at least, the sound is traveling at least 60 times faster than, I shouldn't say at least, but roughly 60 times plus or minus as fast as the air is moving. So it really doesn't matter which direction that air is moving. In structure-borne, here we have this pump, and it has, so this is electric motor, not a pump. Why did I say pump? It looks more like electric motor. But anyways, if it's rigidly attached to the ground, it's gonna vibrate the ground, and then basically sound moving through structure is vibration, right? That's the structure-borne. So those are the paths we need to deal with. So here we just have a list of equipment that could be noise and vibration sources. So fans, compressors, pumps, transformers, other things, cooling towers, condensing units, etc., etc. Turbulent flow, this is another, so this is going to be what's happening in the ductwork or as the air is leaving or entering the ductwork. You have air that's going too fast and you have too complicated of turns. You don't have full radiuses. You don't have the proper separation between them. All like those, if you have that complicated ductwork in the high speeds, you get turbulent noise that propagates through the ductwork just like the fan noise does. Fluids and pipes could be there too. You don't want to be sitting in a restaurant and all of a sudden, the wastewater from the toilet goes past your table. I've worked on projects where that was almost missed. Don't want to do that. And then another source or phenomena that you should be aware of is crosstalk. So this is where HVAC ducts connect spaces. So you might have one supply line that just goes over a row of offices, and each one has a diffuser, right? A diffuser takes off and goes down to supply each room. Well, somebody talking in one room, that sound goes up, travels through the ductwork, and comes down the other. That particular case isn't so bad, especially if you have some lining or some flex duct that connects the ductwork to the diffuser. Likely not a problem. But when it is more of a problem is when sometimes they'll supply to each room, but they just have that one central return, kind of like we were talking about here. So they'll just, above the office door, they'll just cut a hole and they'll put just a grill there. So basically, if you say you had these walls for getting sound isolation, you've got special glass that attenuated the sound more, you got a nice solid core door and good acoustical seals around it. You did all that stuff to get good isolation for this conference room, and then the mechanical engineer just comes along and cuts a big hole in it to let the air go through. That you don't want to do. So you short circuit all that isolation. Now we're going to talk about some criteria. First, we have noise criteria curves, or NC curves. This is just a single number rating system. This will make more sense on the next slide, but it's a family of curves with shapes similar to A weighting. So let's just go and look at it. We'll come back and forth. All of these are those family of curves that are similar to A weighting, right? We're less sensitive to low frequency sound, more sensitive to higher frequency sound. So they kind of follow that same shape. So they're going to be numbered 15, 20, 25, 30, 35, 40, and so on. So the NC rating of noise in a space is going to be the lowest curve not exceeded by noise. So again, if we come here, this line, the dots, that is the noise measured in that room or predicted in that room. So you want to find the curve. So you're not going to have like a 42.6 NC. It's always going to be just an integer. But if you had, so here 43 is going to be the lowest NC curve that's not exceeded. So that would be the NC level for the space. So this point right here is what's dictating the NC level. Oops. So it's widely used, it's easily understood. The bad thing about it though is it's the representation of noise characteristics, say whether it's rumbly or hissy or tonal, that ability is limited. Essentially, it's non-existent. So that's why things like the room criteria or RC curves came about. There are some similarities. So it's a single number rating system, but the difference is here we have a qualitative indicator. So that the part about it being rumbly, hissy, tonal, or even rumbly and loud enough to produce noticeable vibration, we have all these characteristics that are applied to it. Neutral would be the good one. There it basically follows the spectrum of of human sensitivity. So no low end or high end or tone sticks out, which is usually more annoying. So you want neutral. So here an example, RC30N would be good for a school. And that RC rating, the number, that is the average of the 501 and 2 kilohertz octave bands. I probably said that in a confusing way, but I think you understood what I meant there. So you average those 3 octave bands, and whatever that number is, that's what your RC level is. And then based off of that point, there are going to be limits, some spectral limits. So it's a certain amount above at lower frequencies, a certain amount above at higher frequencies. If your data exceeds those, say it exceeds it at the higher frequencies, then you would apply that H for hissy. If it exceeds it at the lower frequencies, you'd apply the R for the rumbly. If it exceeds it at one frequency band, one octave band, and then the octave bands on each side of that are lower by a certain amount, it's tonal. So this was the preferred method compared to NC curves, and there's kind of just like a newer version of this, which is now the preferred method, but for a long time this one was the preferred method. I don't want to say this in the wrong way, but what I wanted to say was that it never really took off very much. I don't know if that's the most accurate thing, but maybe a better way of saying it is that most engineers, most consultants, and most manufacturers of equipment always use the NC. They never really switched over to the RC. And I think the reason for this is that RC can be pretty misleading. So just as an example, you could have really low noise in these 3 octave bands, but you have a really strong tone. If you have that, so RC15T, somebody might see this and see RC15, and they might think, hey, this is a lot better than this RC30, or actually down here I wrote RC35N, but whatever, 30, 35N. They might just look at these and they might not really know how damaging this T is. This T, like say this RC35N, that might be NC35, but this tone might make it RC40 or NC45, and you wouldn't even know that it would, or you wouldn't know how problematic this is. If you had a tone that was really loud, this would be completely misleading. It'd make you think it's fine, but this would be really bad. So I kind of think that because of just the simplicity of the NC curves, that is what everybody to this day, I shouldn't say everybody, but that is primarily what people use, despite this one being the preferred method. Before we go on to this next one, I want to show here it is. So this is just a calculator. You can put, so a lot of times if you make a measurement, you get your data in 1/3 octave bands. So that's all over here. So say I'd make a measurement, you can put in the data that you get just raw from the sound level meter here. This converts it into octave bands. And then over here on this slide, I can pick. So here it's going to determine what the RC rating is and what the classification of it should be. So this was for some military barracks on Camp Pendleton. But the duty bunk was 29N, so that would be good. Let's look at some of these others. Some of these I can't even remember if these were like good or bad. If they were bad, then it was before we fixed things. But actually, this this project did have a few noise problems, but we ended up fixing them without too much trouble. Anyways, corridor was 35R. So that rumbly there. So this is one of those cases where that's pretty kind of misleading. This R down here is pretty big. It's not too bad. This is still pretty good actually. But here we have 35R. Multi-purpose room. So that's good. I guess because so I should explain this a little bit more. This is that line. So we take the average of these 3 octave bands. That gives us this number. That dictates where this line ends up being. Actually, let me even say this in a slightly different way. None of that was wrong, but I skipped something. So we have the 500, 1,000, 2,000. That we take the average of those, and that becomes, so that's this line. And then this line here is based off of, so you have the slope and it intersects that RC level at 1 kilohertz. So from there, you end up having this criteria here and this criteria here. This would make it, if it exceeds this, that makes it hissy. If it exceeds this, that makes it rumbly. And this up here, if you get up into this, that would mean rumbly with perceptible vibration. Actually, that's really quiet for a kitchen. But this one does have this tonal one here. See the T showed up? If one particular octave band sticks out too much compared to what's on the sides of it, then you get the tonal. Checking the time real quick. Don't want to make this too long for you. So now we have the RC Mark II curves. This is similar to the RC curves. It's just kind of the newer, more improved. I don't know that this one is really gonna like take over. From so far from what I've seen, even though this is the preferred one, it's still not as nearly as widely used as RC was, and RC wasn't nearly as widely used as the NC. So as you can almost say, the more one of these is technically preferred, the less it seems people actually use it. So there's probably some psychology there, but no, there are practical reasons for that, like I said. But this one, so they have an improvement to the representation of noise characteristics. They have a low frequency rumble, mid frequency rumble. They have the different categories of noise induced vibration. Said that, so there's an example 1 in the handbook you can look at if you want to see how to determine that. This slide just shows, so this dark line is a pretty typical noise spectrum in a room. It's always kind of interesting to me how a lot of this works in a somewhat convenient way. Even if you didn't have an acoustical consultant on the job that really like tailored the noise, you would still get a shape something like this. So first let's talk about what it makes up. You have the A, which is the fan noise. That's more like the lower frequency rumbly stuff. And then B, so VAV, that's variable air volume. A lot of times say you'll have like one big air handling unit and it just supplies for the entire building. And then these variable air volume units, they're kind of like dampers that are controlled. So you can have a big control system for the building. And say if a certain room or certain zone needs more cooling or more air or whatever, then the VAV will open up. So you can control all the different spaces individually, even though you only have one big air handling unit. That's what that VAV does, and that's more the mid-frequency noise. Um, a different alternative to that might be like having a fan coil unit. So you might have a zone of say like 5 offices and they're all served off of one fan coil unit. That also would be here. And the C is the higher frequency stuff. That's the turbulent noise, say, at the diffuser, that grill that the air comes out of in the room, and the elbow right up above it. There's turbulent airflow noise generated right there. That there's not much you can do about it at that point other than slowing the air down. So that turbulent noise is what makes up this higher frequency part of the spectrum of noise in a space. Now getting back to the part about how I just always think it's pretty interesting how all this stuff just like fits together like puzzle pieces almost. Just the fact that this is what the noise usually is, and this isn't so far off from the human perception of sound. It's probably a little bit more exaggerated. Like we have 30 decibel difference. Actually, no. So at 63 is that like the 26 decibel reduction for the A weighting. That's this, right? So it's almost that we're bringing things down. The main point is it's kind of following the A weighting shape. It's kind of following human sensitivity. And I just think it's kind of interesting how a lot of that stuff just kind of conveniently works together. It doesn't mean you don't have to do anything. I mean, I've spent hours and hours and hours, months or years of my life probably analyzing these types of systems. So there's still a need to analyze it. It's just there's some kind of fortuitous things that just show up here and there. They're interesting. So this slide is frequency ranges of likely sources of sound-related complaints. So if somebody is going to be in a space and they're going to complain about the noise, then depending, or say if it's at this really low frequency stuff, then it's probably the throb of turbulent airflow and fan instability. So say you have like a fan that's not balanced, and as it rotates, it's every time it goes around, it's driving into the ground and causing some vibration that goes throughout the building. Then coming up in frequency, we're still poor vibration isolation, turbulent airflow. This would be more not just that diffuser at the very end, but say like right as you're coming out of the air handling unit, you have to do a bunch of complicated turns and you don't have space to make those turns radiused, then you could get a big rumbly turbulent airflow noise. The roar, so up here we're getting more into like the octave bands that we're often looking at. It's kind of hard to do much analysis below 63. There are rules for getting the vibration isolation right, but for the prediction of like airborne noise and stuff like that, that 63 is kind of the boundary for that. That lowest frequency stuff within that range is going to be fans. So again, turbulent airflow is in here still, but say big fans of an air handling unit, that's going to produce a lot of low frequency noise that would kind of be described as a roar. Hum and buzz, we still have poor vibration isolation. Here we're getting more into those fan-powered VAV units. Fan coil units, VAV units. Whine, so pumps and chillers, these produce a pretty tonal, annoying whine. Sometimes, like chillers, so they're putting here in this 250 to 1,000 hertz, maybe more like down here around 125. Sometimes that tone of chillers is more in here, and the airspace mass of windows will let it. I've seen a couple projects where those just perfectly lined up. They have a big chiller sitting outside with a bunch of compressors in it. It's whining away at a certain frequency, and then So there's this one project I worked on once, long time ago in San Francisco, and they had a chiller right outside of the building, and they had just old single pane windows, and the chiller was never a problem for them. And it's not like, I mean, San Francisco, it's not like you really need to have, a lot of times, like buildings, even new buildings, won't have air conditioning. When I lived there, I don't know if I ever turned my heat on, or I never turned I didn't have air conditioning. I never turned my heat on. It was just that temperature all the time. Um, so it's not like you had a big need to get insulated windows, but for whatever reasons, maybe just the older windows were getting bad. They just didn't want to look like they had single pane windows, but they switched out their windows for what they thought was going to be much better, newer, better thermally insulating and better acoustically isolating windows. But they put in these windows, and so they're insulated. You have a pane of glass, you have an airspace, and you have glass. And the mass airspace mass resonance, remember we just learned how to calculate that when we were predicting the transmission loss of a double leaf partition. So it just lined up that resonance was the same frequency of the compressor's whining. And that whine just went right through it. And everybody inside was incredibly annoyed all day long by it. And they really didn't like what I had to tell them that day, basically. It's like these new windows you put in are just created a really big problem for you. Like you thought you didn't really have a problem. You thought you were going to make it even better, and all of a sudden, now you have a big problem. And there were, like, other than ripping the windows out or going to adding in like a third window. We talked about that interior acoustical sash, just another pane of glass separated by a much bigger airspace. If they didn't do something drastic like that, they just weren't going to get rid of that hum. They could go and put blankets on the compressors, but that only helps a little tiny bit. It hardly helps at all. So anyways, I digress. The hiss and the whistle, these would be grills. So like the diffusers, water valves, that's where you're really going to get the high frequency hiss and whistle. So here it's basically just showing. So here we have the terminology for the different noise from the previous page of what somebody might call you up and say, I hear this rumble. Can you come help? So that is likely these octave bands here. This slide is telling you what equipment produces the noise in those octave bands. So diffusers, we mentioned that. I think I've said all this stuff. I think you probably have a pretty good handle on it. If you need to, like, pause it and read through those, but I don't think I'm going to read through all of them for you again. Not again, but I think we've said those things enough. Here, so this table is criteria. And when we were at the Fork and Spoon, I may have actually brought this out and showed you. I might have brought it up on my iPad, but there we use the meeting and banquet rooms. So there's not particularly like a restaurant here. But the Fork and Spoon, they do rent that space out as like a meeting/banquet room. So this is pretty appropriate. But see, the NC and the RC are in the same column here. That would be 30 NC or 30 RC. It really should be RCN to make a 30 acceptable. This can be kind of confusing. You can have a RC20 and it can be tonal, and it's going to be much more annoying than RC30. So here we have dBA 35. That's another way of doing it. So NC and dBA don't precisely track. Like if we go up one here, we're not going to go up one here necessarily. We might, but it might be different. We might go up 3 over here, something like that. it's kind of the way things work. If it shows up in actually if you're at NC 30 and it's being driven by lower frequency, you might go up 1 decibel and it like let's go. I think we had that, didn't we? Yeah, here. See, like it's not. This isn't 5 decibels here. You're going up 5 NC. Like here, it's more truly 5 decibels. But over here, it's not. You're going from NC 50 to NC 55 in just like 2 to 3 decibels. So say you went up 1 here, that might raise your NC rating 2 dB. But your dBA, say if it was this noise spectrum, raising this up 2, it might not affect your dBA at all, because your dBA is probably going to be driven by these, and then that curve comes up like this. So they don't necessarily track you. What's shown here is just kind of like a middle of the road relation between these. This I would say that your dBA could be as low as your NC, and it could be as much as 10 decibels. It's usually probably between those ranges. And remember dBc, that just accounts a lot more for the lower frequency. It gives more weight to the lower frequency sound. So that's why higher values are possible over here. Maybe we should look at this and point out some of the more critical things. So 25 is probably going to be the quieter end on here. We have 20. So drama theaters, concert, and recital halls, 20. Recording studio would be 20, maybe even 15. If you're really doing the highest end recording studios or concert halls, you probably want to get down to 15. So general assembly with critical musical programs, this might be like a high school auditorium or a church, be 25. Classrooms are 30. If you had, so in a residence, a private living area would be 30, but if it's more like the bathroom, that could be, or the kitchen, 35 would be okay. Offices, if it's like a private executive office or teleconference room, you might be at that 25 to 30. And then if you went up to like just a basic private office, you can be 35. I guess they still put that in 30, but usually 35 could be okay for that if it's not executive. Open plan offices, you're at 40. When you get up to 45, that's more like, say, like a laboratory or extensive phone use and speech communication. Gymnasium, so say it's like meant to play basketball, something like that. If you start getting up above that, it really gets to the point of where you need to have, like you can't have much more than minimal speech requirements, right? It can't be a space where people need to talk all the time and easily be understood. So let's cover this slide, and then maybe it'll be good to stop. We're basically at 50 minutes right now. You know what? We'll come back with this one. That's it for this lecture. We're at 50 minutes. So have a good day. We'll talk to you later.